All right, on ideal gases and gases in general, you remember that I said an ideal gas is a concept, that we don't actually find ideal gases in the physical world. It's an idea, but that the physical gas that approximates ideal gases best is helium, particularly at low pressures, and 1 atmosphere is a relatively low pressure. So we've got something, the closest possible thing to an ideal gas here in a real gas. So first we're going to find the number of moles of gas we've got present, so that's part one. Well, what do we know? We know that the pressure is 1 atmosphere, but just let's hang on for a second while we figure something out. We have a pressure, we have a temperature, we have a volume. We are interested in knowing the number of moles of gas present, so N number in moles. And the ideal gas constant R is equal to 8.314 depending on the units. You'll remember I mentioned in the lecture that the units that we use for all of these other things will change the value of what that constant is, so depending. So the value I'm using is 8.314 litres kilopascals per Kelvin per mole. So I'm using those particular units, so that means I have to measure my volume in litres, my pressure in kilopascals, my temperature in Kelvin, which I should always do, and my number of moles in moles, which just makes sense. So it's the pressure and the volume that are really interesting. So the volume in this case we said is 2 litres, so it's already in litres. I don't have to convert from cubic meters or any other unit. The temperature is 273 or 293, just checking, 293 Kelvin, and the pressure is 1 atmosphere, but we do have to convert that one, and 1 atmosphere is a pressure of 101.3 kilopascal. So you can see why when I started to write down the pressure, I suddenly remembered, hang on, let's check which constant I'm using and therefore make sure that we get things in the right units. All right, so I can use PV equals nRT, the ideal gas law. I can rearrange it to make N the subject, so N equals PV over RT equals, what's my pressure, 101.3 times my volume, 2 over my constant, 8.314, times my temperature, 293, will mean that overall I have 0.083 mole of gas present. So that's the number of moles of gas in my sample. Okay, so that was relatively straightforward. Now, the second part we can approach a couple of different ways, and I've tried to remember to keep looking at things multiple ways if we can, because students will attack them multiple ways. But if you teach them also that they can address the same problem in multiple ways if they understand, then it gives them options and it gets them thinking physics, not just maths, and not just plugging formulas. So 2 ways we can address this question. One is to use the ideal gas law again. So we can use PV equals nRT again. I've been asked, what's the question? If the container is heated to 122 Celsius, well, little alarm bells ring because that's not in Kelvin, so we might have to convert that to Kelvin. What do we need to do? 0 Celsius is 273.15 Kelvin, but the 0.15 can be ignored for most normal purposes. So 273 plus 122 is 395 Kelvin. Big K for Kelvin. So that's the temperature we actually want, and that's the only thing that's changed. Everything else in our list is the same, except that we've changed the temperature, kept the volume constant, and we want to know the new pressure. So we can rearrange this a little bit. P equals nRT over V equals 0.083 times 8.314 times our new temperature, 395, over our volume, which is unchanged at 2, equals 136.3 kilopascals. Now, we started at 101.3 kilopascals, and now we've heated it up without making the container any bigger. So it makes sense that the pressure has increased. The pressure has gone up by about a third, given that the temperature also went up by about a third, because we were at about 300, roughly about 300 Kelvin, and we've gone to roughly about 400 Kelvin. So that makes sense. It's all proportional. It hangs together. It hasn't multiplied by 100 times. It's gone up by about a third when the thing that we changed went up by about a third. There's a different method we could use, though. We used the ideal gas law. We could use the combined gas law. So if we use, this is the second method, P1V1 over T1 equals P2V2 over T2. Now you might remember I said I find it simplest to remember this one rather than Boyle's, Charles and Gay-Lussac's law, which are all subsets of this. Now in this case we haven't changed the volume, so we can just get rid of the volume. We don't care about the volume because we haven't changed it. We've changed the temperature, and we want to know what's happened to the pressure. So let's rearrange and make P2 the subject. We're interested in the pressure at time 2 after we change the temperature. So that's going to be, if we do the rearrange, P, I don't know, I keep doing R's instead of P's, is going to be P1 T2 over T1. That's going to be that rearrangement of that to make P2 the subject. So P1 was our initial pressure, 101.3 kilopascal, times T2, our new temperature, 395, over T1, our old temperature, 293, equals 137 kilopascals within rounding, and within rounding error, that's the same answer as we got up here. I've obviously rounded something. It's within 1. I've obviously rounded something a little differently on the way through. And we've ended up with basically the same answer by using 2 different methods. Now, if you're marking and you mark it wrong, if it's off by this much, I would be worried, because you're making that same judgment. You know, it's probably something that's been rounded somewhere and not rounded somewhere else, or something like that. So it is, for all practical purposes, the same answer arrived at by 2 slightly different methods.